Great. Thank you, Aaron, for bringing us all together today. Indeed, as Aaron said, I'll dive a bit more on the quantum side of today's discussion and give a few use cases in genomics that I've been researching for the last about 3 years. So before we go into that, let us map the current research themes that is there in quantum mechanics and some of them in quantum computing as well. So first and foremost, we need hardware to run any computation on. So we need a quantum hardware. So that comes from mainly two different types of research fields in that. One is making the qubit. So that is making the quantum bits or really the quantum processors. And then we need the architectural stack. So once you have the quantum chip, you need many different levels of abstraction that I'll again discuss later that translates this quantum logic to this down to this chip. So you start off with a very abstract logic of let's say an algorithm, and then it goes down down these different layers of abstraction ultimately to run on some kind of an analog device that is the quantum chip. So that is from the hardware angle, but for today's discussion, it's more like we want to discuss more on the application side. So the applications can be divided into different kind of themes. One of them is quantum communication and cryptography. So there's where we use theorems or the proofs from quantum information theory to have a secure communication channel. And that seems to be quite relevant for biology or bioinformatics applications, because you really need to transfer the secure data from the patients to the hospitals to the doctors. And what's more more private than your own personal data. So it needs to be really, the communication channel needs to be really secure for that. Then we have the molecular simulations, and my guess is this is one of the more near-term applications where we will already see quantum computing giving us results better than classical computation can ever. And the molecular simulations for biology will mostly be used for drug discovery and drug design, and also for protein folding. And the basic idea is you have an energy landscape of all possible configuration of that physical system or the chemical system. And you want to figure out which is the lowest energy state, or which is the natural state of how that compound is going to react with another compound. So that's basically what's used for drug design. Then we have the quantum sensing, and Aritra already talked quite a bit on that, where quantum computing or like quantum devices can be used for better understanding the different physical phenomena and to get information out of them. And this quantum sensing can already be applied to genomics in a way that we can use the phenomena of quantum tunneling to design what's called as a nanopore sequencing. So we can get better data out from the DNA using quantum mechanics. So this is not per se quantum computing, but using, again, the core principles of quantum physics to design better instrumentation. Then we have optimization and learning. I'll be talking more on this one. So that's why you see that in color. So this is mostly about the data crunching, and today's world is all about processing a lot of data, what we call as big data. And then there are different sources of this big data, and some of them are like the EEG, which is the signals that come out from our brain. Then we have the MRI, then we have the protein-protein interaction between, let's say we'll talk more on that later. And then we have the foundation. So that is more the bridge between the philosophy and physics, also applied to biology. So we find in that different phenomena in nature, which also uses quantum mechanics, like in photosynthesis or even in the navigation of birds, we see a lot of quantum phenomena popping out. So I started out my research, again, around 3 years back on quantum genome sequencing, that is to process the big data problem in genomics using quantum acceleration. So once we have the algorithm, we want, again, a system to run that algorithm on. So that's where the quantum genome accelerator comes up, where we want to take that high-level algorithm right down to the chip level. And for the last an year or so, I'm looking more into quantum genome analysis, where the sequences you want to analyze and figure out some patterns and understand what the DNA code stands for. So that's basically getting some meaning out of that data. Unfortunately, quantum computing is not the magic pill for every single problem, because we already have very good classical computer developed over almost a century now, which can already take us to Mars, let's say control a Mars rover, or even better, the best human chess players or Go players on Earth. So the normal classical computers are already really good at a lot of stuff, but there are some things which classical computers can do, but not the best in. So those are what we want to find other technologies to just offload them to. And there are these accelerators. There are many different types of accelerators again. So if you are a game addict, a computer game addict, you're always after the best graphics card that's there in the market. So the graphics card basically has what's called as a GPU inside it, or a graphics processing unit. So when the CPU, the normal classical processor that you have, has to do a lot of graphics processing, let's say while playing a game, the CPU offloads that particular part of the task to the graphics processing unit. And the graphics processing unit is specially designed to handle such kind of computation, and thus makes the computation faster for you. You are able to play the game. So that's pretty much the model that we expect for quantum computing to be there in the near term, and possibly for a very long time, that the quantum computer will also be an accelerator, as you see over here, where we want to offload only the tasks which quantum computers excel from classical computing to, whereas all the other normal tasks like playing a game or doing normal calculation still stays with the classical computers that we have in our laptops or supercomputers. So there we see that quantum computing will be, while it's a better model, more universal model of computation, in the near term, we are not going to have an universal quantum computer that's going to do everything that we do on classical computers, but only the small part, which is really, really difficult to do for classical computation. So when a computer scientist says efficiency, they normally mean that how much time it takes to do the computation, or how much memory or how much RAM you need for the computation, or can you explore a better solution space out of that exploration. So that's when applied to genomics. For example, when you want to do the genome sequencing, that can already give us an advantage that take us from, let's say, something like 18 hours that it takes to do the genome sequencing of one single human being to down to 2 hours. So that's what a computer scientist can tell you. And one of the reasons why we are having this meeting today is we need to collaborate a lot with domain specialists to understand how this translates, how these numbers translate to what application or one new kind of application we might have with these kind of speedups. So if you ask me, I can tell you that with quantum algorithm, if you have a big enough quantum computer, you can get a 2-hour speedup. But I have absolutely no idea how that's going to be used for medication. That's again why we need a lot of collaboration in this field. Where do we stand now today? So as a computer engineer, my work is to bridge the gap between the software and the hardware again. And as I said, that the architectural stack has many different layers. So we start off with the algorithm. Then we have the programming languages in which we code our algorithm in. Then we have the compilers, which translates the algorithm down to the specific electrical pulses, which ultimately go down to the quantum chip, which is normally housed in a cryo refrigerator. The problem with that is right now, as standing today, there's a huge divide between the quantum software and the hardware. So while there are a lot of different options for quantum hardware, we really do not have what is like the transistor for classical computers. On the other hand, we are always in search for the killer application for quantum computation. We know a lot of applications have a lot of possibilities, like breaking RSA, for example, in the long term. But what will be the first quantum application that's going to be, what's going to show the quantum advantage is still not really clear. And a lot of people are exploring this stack from the top down, looking at different applications. So at our department, we were initially looking at different ways of designing the architectures such that any algorithm can be taken to any chip, whatever comes up in the future. So that's one way to do it. You make your microarchitecture in such a way that a single program can be targeted for different underlying technologies. But you can also do it the other way around, since we do not really know when we'll find that the transistor of quantum computing. We can also work with quantum simulators for the time being. That is, we have everything down to the microarchitecture, but then instead of running on a real hardware, we run it on a very small classical simulator. And in that, we again need a lot of interdisciplinary expertise, because now we are looking at the top layer of the stack where we need to interact with a lot of domain specialists. And then we can simulate it on a very small use case, get a lot of confidence that it works, so that the moment you have a big enough quantum computer, you're good to go. You get that speed up that you expect from the quantum computer. So that's the model of working that we are working in our research group right now. So why look at genomics in the first case? So that's what I research in. So these are the three graphs. And in the COVID era, you must be all very familiar with exponential graphs and how logarithmic scales work. So these are all these graphs are in exponential scale. And we see that this blue dots that you see in the first graph over here, it already shows a slowdown of how fast computers are getting. So that's called as the Moore's law in computer engineering. And on the other hand, we see that the genomics data that gets generated from the sequencing machines are also growing at an exponential rate. But the problem is the way that exponential graphs differ in is this is, again, an exponential scale of this growth of computing power, but this is the exponential reduction in cost of genome sequencing. So that's, both are exponential, but they are in a different exponential scale. So the gap between the amount of data that gets generated and the amount of processing power that we have to crunch them, the gap keeps getting bigger and bigger. So we need some radically different technologies to deal with that, to deal with this kind of data. That coincides pretty well because one of the, again, market analysts, Gartner, suggested that these kind of technologies that has biology applications and quantum match very well. So we see a lot of fields in quantum computing which has a lot of correlation with biology and genomics and pattern matching, for example. So this was my primary inspiration, but then again, you need to try and do it before you can really understand that something's going to work. So I'll just quickly go through some of the three research projects that I've worked on so far. The first one is to get the data out, so genome sequencing. So we have, let's say, an organism like a human being or even a crop like rice, and you want to get the DNA out of that organism. The problem is the DNA is a very long molecule, so you cannot get that out at one go. What you get out of the machine is the small reads, a bucket of very small pieces of that DNA. But then to make any reasonable inference out of that data, you need to piece them back together. So that's exactly like solving a jigsaw puzzle, where you have a reference DNA of that organism, and then you take each of those small pieces and find where it fits in the reference genome. And then once you have the big big stitched data again, you can go ahead with the analysis of that DNA. The problem with that in classical computing is even piecing out and solving that jigsaw puzzle is incredibly difficult, even with supercomputers. So there are a host of different algorithms getting invented every single year. There are 90 plus read aligners, what we call them. And the problem is not one size fits all. So each of them has been heavily optimized to either work on a specific type of computing architecture or to handle a specific type of genome. Maybe one of them works only for bacteria. One of them works only for cancer cells in human beings. So we do not have one size fits all unless we look at an enormously difficult computing power, which is, let's say, the quantum algorithm that I worked on. So the idea is very simple. You take a very basic version of this problem, which is like you have the reference genome over here and you have a short read. And what you basically accelerate on the quantum algorithm is kind of the version of the linear search that we do. So you take the short read and you match at every point on the reference genome. And if you tell that to a classical computing, classical genesis, they're just going to go crazy because this in classical computing is very inefficient. But then again, where you have the quantum advantage that you can match this small part in the reference genome at the same time using the superposition. So you get the place where it matches the best using the quantum computing principles. Again, this can be applied for very different kind of technologies where instead of, let's say, the genome, you look at the stock market. So you have then a pattern-based trading application. Okay. Coming to the next application, then the first question that we were discussing in the last slide is we need a reference to do that pattern matching. So where do we get that reference from? So when the first time the human DNA was sequenced, it didn't have a reference. So we had to make a reference from a much more difficult computation process. So that's called as de novo assembly. And this is how it goes. So you have, let's say, 4 DNA samples over here, 4 of those short reads, and they need to be matched end to end. And you do not have a reference. So this is basically what we want, where the green is matched to the green, the yellow is matched to the yellow, the blue is matched to the blue. So how do you do that? And the space of possibilities, again, increases exponentially. Let's look at some of the example, this example over here. So let's say we have this 4 DNAs over here. So one way to match it is you just join the arrows like this. So you see that in this, it's not a very good matching because the green is now matched to yellow. This one is good because the blue is matched to blue. But then again, these 3 possibilities are bad. They're not matched in the right way. And you see that there are totally 6 possibilities in which this can be done. And one of them is the right one. Like this is where it is matched in the correct way. So this is again where we use the quantum superposition principle, where we explore all these possibilities of these kind of routing maps in quantum, which can be either a quantum annealer or a variational quantum approach. Again, this problem can be applied to many different optimization problems, which can be in warehousing or in traffic routing, or even for DNA design. So the last application is pretty much what I'm working on and very excited right now to work on. So this is mostly where the word metabiology comes from, which is one of the founders of quantum algorithmic information theory, Gregory Chatin's proposition, where you take the DNA, we colloquially call the DNA as the code of life. But in this example, you take that in a very literal sense, and you treat the DNA as a program. So when the cellular mechanisms work in the cell, it's read like a program by the RNA. So there must be some programming structures that you can detect in the DNA, things like loops, things like decision statements, and that gives rise to some causal models that you can infer from that interaction between these sequences, and already get a better model of how the organism works. So that's exactly what Araceli talked about, what is life. We can really understand the meaning of how life works. Again, this looks very theoretical, but it has already been applied in classical computation. So this is a map of the protein-protein interaction between the coronavirus, the SARS-CoV-2, and the human proteins. So what this research does is try to map out which protein of the virus interacts with which protein of the human cells. And is there an algorithmic relation between them? Is there some pattern between a protein in the virus, between the ones that interact in the virus and in the human being? And they found quite positive results in that the more complex protein in the virus happens to be the ones that interact with the more complex protein in the human cells. This is also what I'm working on right now. And surprisingly, the same approach has a lot of application also in artificial general intelligence. That is the theoretical model of artificial intelligence, and also in theoretical physics, like in the holographic principle or in tensor networks, for example. So I'll just end with a quote from Stephen Hawking, the renowned astrophysicist. And he said that science is beautiful when it makes simple explanations on phenomena or connections between different observations. So the highlight is on simple, and that's also how this method works. It tries to find out which program is simple enough to explain a phenomenon, and that happens to be the best way of explaining how the data works. And then he goes on to say that examples include the double helix in biology and the fundamental equations of physics. While we might not have found a relation between these two yet, but it's really worth exploring that in the term ahead. Thank you for my presentation. And I think we need a lot of collaboration between many different people over here, and it's great to have this talk. I'm looking forward for a lot of collaborations in the future. Thank you.